And here we go with section 9.4, nearing the end of the chapter and nearing the end of the school year. How about that? And we start off looking at theorem 9.4, but before we look at theorem 9.4, we need a definition. Definition. Arc RS, the red arc, is the something or other of chord RS. Remember what a chord is. A chord is a segment that connects a point on the circle to another point on the circle. That's a chord. This is the arc. So we say that arc RS is the arc of chord RS. Very simple. So RS, the arc, is the arc of the chord. Or you can reverse that and say that the chord is the chord of the arc. It's kind of like they're buddies, they go together. So the chord belongs to the arc belongs to the chord. The chord is the chord of the arc, and the arc is the arc of the chord. Right. Now, based on that, consider this. Suppose I take another arc that is congruent to arc RS. Right there. Let's take that arc, move it over here, and I'm going to rotate it around, and I'm going to fit it to the circle someplace over here. So we would have to agree that because I actually used my electronics here to make a copy of the red arc, we would have to agree those arcs are congruent. So arc RS is congruent to, let's give it a name. Did the book give it a name? Over there on page 344. Yes, they called it arc TU. Arc TU. Okay. So if we now connect points T and U with a segment, or I should say, I suppose, with a chord, theorem 9.4 says that congruent arcs will have congruent chords. And the converse of that, congruent chords will have congruent arcs. So, for instance, if segment RS happens to have a length of 12, and segment TU also has a length of 12, then we know that whatever this measure is, it has to be the same as that measure, because congruent chords will have congruent arcs. And likewise, if we knew the arcs were congruent, then we can conclude that the chords must also be congruent. All right, simple enough. Let's move on. That's all there is to theorem 9.4. Now, another definition. Now, this definition is going to sound very familiar to you. If arc XY happens to be congruent to arc YZ, then point Y is called the, and you can probably guess, it's called the, wrong word for now, the midpoint of arc XZ. It sounds familiar because we had the same definition for segments. If you have a segment, remember, and it just happens that this piece is congruent to that piece, then we call that the midpoint. That was the definition of midpoint. Remember that old expression we have. What makes a midpoint a midpoint? A midpoint creates two congruent parts. That's the definition of midpoint. Two congruent parts. Same thing with midpoint of an arc. Two congruent parts. We can signify that on the diagram the same way we do with segments, with a little dash on each part. So if arc XY is congruent to arc YZ, then by definition, point Y just became the midpoint of the arc. And by the way, any line that happens to go through that midpoint, that one, or this one, or this one, any line that goes through that midpoint is known as a bisector, because what does a bisector do? It cuts right through the midpoint. A bisector cuts the arc into two congruent parts. Okay, and on that note, we now move on to theorem 9.5. Theorem 9.5 says this. If I have a diameter and some other chord, remember a diameter is a chord. A diameter is just a very special chord. A diameter is a chord that happens to go through the center of the circle. If I have a diameter and another chord that is perpendicular to that diameter, then two very special things happen. This is Theorem 9.5. If I have a diameter, or by the way, it could be not just a diameter, it could be, there we go. It could be a piece of a diameter, or it could be an even smaller piece of a diameter. So it doesn't have to be a full diameter for this theorem to be true. But if I have a diameter or a piece of a diameter that's perpendicular to some other chord, then that diameter will bisect the chord and it will bisect the arc of that chord. So in other words, taking away my clever little marks here, ding, 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 ding. If, for instance, all I know is that this is a diameter, it goes through the center, and I'm told it's perpendicular to this chord. Suppose somebody tells you this has a length of 8. Well, then what's the entire chord's length? The Theorem 9.5 says that when a diameter is perpendicular to a chord, it will bisect the chord. So if that's 8, that must be 8, therefore the whole thing is 16. By the way, historically on tests, a very common and silly mistake. One of those kind of things where you're kicking yourself for messing this up on the test. Suppose these points are called A, B, and C. And I gave you that. And I ask you for the length of AC. It's amazing how many students will look at this question and say, oh, that's easy. If that's 8, then that's 8. And they say 8 without actually looking. They're making up their own question. Don't make up your own question. Read mine. I'm looking for the length of AC. 8 plus 8. It's not 8, it's 16. Or the other way around, I've also had cases where I will ask for the length of BC. And somebody, just BC, and somebody will say on the test, oh, you can't fool me. I know that BC is 8, that makes the whole thing 16. What? Don't make up your own question, read my question. I was asking for BC, which is 8, not 16. Please read my question. Don't make up your own. There's no mercy if you make up your own question. You've got to answer my question. Read the letters carefully and look at the diagram. None of those knee-jerk reactions. Pa-ching! No. Think it through. Read carefully. All right. Likewise, by the way, if we were told this arc has a measure of, say, what's that look like to me? Suppose that arc has a measure of 60 degrees. Why do I say it looks like 60? Because I know that a fourth of a circle has to be 90, and this looks like it's more than half of a fourth of a circle. It looks to me like it's more than half of 90, so I'm calling it 60. Clean that up. Okay. All right, if that's 60, then we need a point name here. Let's call this point D. What's the measure of arc DC? The measure of arc DC would have to be the same as AD, which would be 60. And by the way, please again, you've got to read the question carefully. Don't make up your own questions on the test. What's the measure of arc AC? The measure of arc AC, in this case, would be 60 plus 60 for a total of 120. And here's another question I could ask you. Let's put a little 1 right here. What's the measure of angle 1? Or by definition, an angle's measure is equal to its arc measure. So if the arc is 60, the central angle must be 60 also. So angle 1, measure of angle 1 is 60. Or I could ask you for the measure of angle A. Ooh, I don't have a point name here. Let's call it O. AOC. Well, AOC would have to be 60 plus 60 is the whole arc, so the angle is likewise 120. You just have to be very careful that you don't make up your own questions. Read the letters in the problem carefully, compare to the diagram, think it through, don't rush. All right. Oh, I have a little note here. Somebody says to me, hey, I don't believe this theorem. Prove it to me. I don't believe this is true. Just because those guys are perpendicular, I don't think that means that it has to bisect the chord and bisect the arc. Okay, well that's what geometry is all about, is proving stuff. So let's go ahead and prove it. It's easy to prove. Oh, I lost the center of my circle. Let's suppose it's right about here. All right. I'm going to throw in a couple of radii. Let's put a radius there, and let's put a radius there. Radii are all congruent. That makes this red triangle an isosceles triangle, which means that this angle has to be congruent to this angle. Base angles of an isosceles triangle are congruent. All right, now let's get rid of the red. So we have those two angles congruent. Well, thinking back to the old chapter on congruent triangles, do we now have any way to prove that these two little triangles are congruent? Well, one might say, how about the reflexive property? Well, that would give us SSA, and you should know by now very well that SSA doesn't work. It doesn't exist as a theorem. It can't be used. But wait just a moment. It was given to us, and I forgot to mark it here, it was given that this diameter is perpendicular to that chord. So we have a given right angle here. Oh, yes. So now what do we have? Angle, angle, side, congruent to angle, angle, side. We have AAS. So yes, these two little triangles are congruent. Well, if the little triangles are congruent, then CPCTC, corresponding parts of congruent triangles are congruent, says these segments must be congruent, and we just proved the first part of Theorem 9.5. That this chord is indeed bisected. But CPCTC also says that this angle must be congruent to that angle. And if these angles are congruent, then guess what? These arcs must be congruent. So if the arcs are congruent, then that means that this arc has indeed been bisected. We just proved both parts of Theorem 9.5. That a diameter, when it is perpendicular to a chord, by throwing in these two radii, we're able to prove that the chord has been bisected and the arc has been bisected. Done. Moving on. Here's example 1 from page 345. All right, let's see here. What do we got going? We have a diameter perpendicular to a chord. Well, Theorem 9.5 says that when that happens, then the chord has been bisected, which means that x must be 5. In fact, let me just change that x into a 5 here. So we just solve for x. X is 5. Congratulations. Hey, wait a minute, look at this. This is 10, we're told. And this is also 10. Ooh, don't congruent chords have congruent arcs? Yes. So if this arc is 86, then this arc must be 86. Oh, we're done. Y is 86. No, Y is not 86, because Y being marked here on this part means we're looking for just that side. Well, Theorem 9, did I say 9.5 earlier? It's 9.6, isn't it? Yeah, no, 9.5. Theorem 9.5 says also that when a diameter is perpendicular to a chord, Not only is the chord bisected, but so is the arc. If the whole thing is 86, then one side of it has to be 43. So y is 43. 43 and 43 will give us the 86. Example 2. It asks us to find the length of a chord that is a distance of 5 from the center of a circle with a radius of 8. And they don't give you a diagram. Actually, in the exercises in the book, they will not give you a diagram. The diagram that you see here on page, whatever this is, the diagram for this example on page 345 is part of the solution. It's not given. So you draw yourself a circle. You mark a spot that you're going to call the center. We're going to have a chord. We know what a chord is. We're going to have a chord that's a distance of 5 from the center. So let's draw ourselves a chord here. Any old place. And that chord has to be a distance of 5 from the center. Well, by the definition of distance between a point and a line, it has to be perpendicular. And we're told that distance is 5. Ooh, remember I said that theorem 9.5 does not just apply to diameters, but to any piece of a diameter. So if this diameter is perpendicular to this chord, then we know it must bisect the chord. So these two pieces are congruent. But wait just a moment. We're also told that the radius is 8. Now I've seen students on a problem like this say, okay, the radius is 8. Let's draw a radius someplace. Folks, I ask you this. How much good does a radius over there do you? Well, not much. True, not much. So where do we put the radius that it will actually help us? Make a triangle out of it. Put it down here or up there, I don't care. The radius is 8. Put the radius someplace where it will actually help you, because we're good with triangles. So now we want to find the length of this chord. Alright? If this is 5, because we're told so, and the radius is 8, because we're told so, how are we going to find this white piece here? Haha, yes, it's never going away. A squared plus b squared equals c squared, Pythagorean theorem. Now folks, don't do what some of you did on the chapter 8 test. Some of you ignored the fact that c has to be the hypotenuse. Where is the hypotenuse? It's the longest side. It's the side opposite the right angle. This is the hypotenuse. So 8 goes there. That is important. Some of you blew it on the test because you were putting the hypotenuse someplace else. Then we have 5 squared plus the unknown, let's put a b here, b squared. So that gives us now b squared equals 64 minus 25. 64 minus 25 is going to be what? 39. So if b squared is 39, then b must be the square root of 39. So if b is the square root of 39, then what's the whole thing? Because again, we know that the diameter bisects the chord when they are perpendicular. So this piece, b, is square root of 39. The other piece is also square root of 39. That gives us the square root of, 2 times the square root of 39 for our final answer. 2 square root of 39. And no, that is not equal to the square root of 78. No, it doesn't work that way. 2 times the square root of 39. And I would claim that wasn't so bad. And now we have one more theorem. Here we go. Theorem 9.6. Theorem 9.6 says this. If I have 2 chords, and their distance Remember, distance by definition between a point and a line is perpendicular. Their distance from the center is the same. I'll mark them with congruent marks here. If two chords are the same distance from the center, then those chords will be congruent. Absolutely. And conversely, if two chords are congruent, then guess what? They will be the same distance from the center. If they're the same distance from the center, then they will be congruent. Converse. If they're congruent, then they will be the same distance from the center. It works both ways. And on that note, we dive right into the last example in the section. Example 3 from page 345. First of all, here we have one of the situations again where we have a piece of a diameter because it goes through the center and it's perpendicular to a chord. That means that that chord has indeed been bisected. So if this is 3, this must be 3, making the whole thing 6. But wait just a moment. This whole thing is 6. We're already told that this one is 6. But congruent chords will be the same distance from the center, meaning that x must be 4, because this distance must be the same as this distance because the chords are congruent. Not too bad, huh? And that's all there was to that last example. So we are done with this, and stay tuned for the presentation later of section 9.5, coming to a computer near you.